Good morning, good morning, good morning. It's been a couple of days, but it is really good to have you guys back, okay? While it's nice to have a couple of days off, it is important to come back and be able to pick up where we left off and to continue on with these exponential functions. And this is an exponential function, but it's a special kind of exponential function. It could either be an exponential growth function or an exponential decay function. And in this case, it is an exponential decay function because it is shrinking. It is slowly but surely getting smaller and smaller and smaller and smaller. Okay? Today, we're going to take our exponential functions that we've been learning about for the past couple of days, and we're going to apply domain and range to them. And this is something where I see a little bit more real world relevance when it comes to this. Once again, the domain is going to be all of the x values in a function, and the range is going to be all of the y values in a function. If we're talking about all the x values, we're talking about this side-to-side line right here. Anything that line gets through or anything that graph goes through on the x-axis is going to be included here. And I know you can see that line constantly getting bigger as it pushes off to the right there. But as the line pushes off to the left, you can see where it grows up and kind of slows down. I want you to be very careful with what I'm about to say, because it is very easy to conflate some of the words that we're about to talk about, okay? In this case, this graph, while it looks like it's slowing down, going to the left and such, it is still going to end up going to the left. It is going to continue getting smaller. That means that our domain is going to be where x is, and it's a capital R with two lines in it. That means all real numbers. You may also see that where negative infinity, x, and positive infinity with those less than or equal to signs in the middle there, saying that x is between negative infinity and positive infinity. It could be listed either way, but honestly, all real numbers, or even writing out all real numbers, is going to be useful here. And you may see this in any of the questions that you're looking at on the star or with me. You could use all real numbers, capital R, or negative infinity to positive infinity. The range is going to be where we start getting a little bit crazy, because with that range, it talks about going up and down. And I can see where that graph is up here above the x-axis. However, it slows down as it approaches the x-axis. It actually never crosses the x-axis. It approaches the number 0 on that y-axis there, and it never actually goes below it. That is going to be called an asymptote. asymptote. Okay, it is a limit. It is a boundary that this line cannot cross. And the word limit is actually the math term that we use for this, because it is something that you will see in calculus as well, where it talks about what the limit is, what the actual, we can't broach this line. It's like the speed limit. You're limited to only going 20 miles an hour in a school zone, for example, okay? Now, the equation for that asymptote in this case, because it is the x-axis, is y equals 0. Now, that y equals 0 is important because, again, it is an equation that you'll have seen a couple of hundred times by this point, and so you should be familiar with why it is y equals 0. But on the y-axis, if you look at these numbers 1, 2, 3, 4, 5, and so on, if you wanted to stay at the same height, you could. You would only be allowed to go side to side, though. Like at any of these points along this red line that I'm drawing, it is at 7 up from the x-axis. That would be, y equals 7, okay? But we're not talking about that line here. We're talking about any of these points that are along this line down here, where it doesn't matter if it's -2, 0, or 1, 0, or so on and so forth. That y value is going to remain as 0. So because of that, because y has to be bigger than 0, because it can't go below it, that's actually what we're going to write, is that y is greater than 0. Not or equal to, because it never actually reaches 0. That's the point. When you have an asymptote, it is a line that this graph cannot touch and cannot cross. It's like an electric fence. If you have ever seen somebody who touched an electric fence, you'll know why I say it like that. You don't want to lean against that fence. You don't want to grab onto it. It is going to hurt. That's the same that this graph is doing. It can get close to it. Those cows, they stick their head through those fences to try to get the grass on the other side because that's what they do. They have to reach for the grass that's on the other side of the fence. They'll eat everything right up to that fence, but the moment it comes to actually touching that fence, they will not do it because they don't want to get shocked. This graph has that fence at 0. At y equals 0. It'll get really close to it, but it's like it's kryptonite. It will stop before it actually touches it, okay? So here, when we start looking at this graph, we are able to start filling in this table as well as we are able to start graphing this equation, all right? This is something that I did show y'all last week, but I will give you a visual example of this week. So give me a second to jump across to my camera and let's go ahead and get this started. Take your calculator, turn it on. If it has to refresh, it is what it is. I am very sorry about that. Oh, yeah, batteries. Gotta love batteries. Let's see if this one will work. Okay, calculator's on. You're gonna press B for graph, and you're going to be able to delete all of this. Menu, 7 for that table, and then 2 to remove that table. Menu, 3 because you want to graph a function, so 1. And you're gonna make sure that you're not on F2x, that you are on F1x. And you're going to delete all the stuff that's on there. Give me a second as it resumes. If that pops up, you can press escape to cancel it out. The equation here is going to be y equals F1 of x equals, can stay like that, 8 times, open parentheses, half, 1, delete, because I don't want that parentheses there. I want to have the fraction, close it, raise it to the x, and I'm going to use that x on the bottom, and that's going to be the equation that we were looking at here, and we hit enter, and it gives us our graph. Menu, table, so 7, 1, because I want to see the table, and now I have this graph where I can scroll up and down through this and see what these numbers look like. I can even see what the graph looks like, okay? So I'm going to take this information here that you should have been poking along with me. If you didn't actually push these numbers in, I'd ask you to pause the video, rewind it a couple of minutes, go back to where I put it in and follow along, because we're going to start filling in our table, okay? So when it says x equals -1, we're going to go on our graph to where x is -1, okay? Like literally, we're gonna take our table, we're gonna look at it right here, and we're gonna say x is -1. And I'm gonna see that 16 here. I'm gonna see where 0 is 8. I'm gonna see where 1 is 4 and 2 is 2. And I'm gonna take those over to our graph here at our table. I'm gonna start typing this in, where -1 is 16. And then I have 8. And then I have 4. And then I have 2. It's getting a little out of line here. I apologize. So let me see if I can highlight everything. Come on. You can do it, buddy. Highlight everything. Highlight everything. It ain't working. Nah, it ain't pulling any closer together. Whatever. All right, I'll just keep it going. For that 3, I'm gonna end up having 1. For the next one down, I'm gonna have 0.5. I'm going to have a 0.25, not 0.25, 0.25, and I'm going to have a 1.25 or 0.125. All right, that's going to fill in this table over here. Our goal from here is to be able to graph it. So I'll take each of these points and put it in at negative 116, at 0.8, at 1.4, at 2.2, at 3.1, at 4.5, and it's going to slowly get flatter like that. And you'll see how this graph is an exponential function. Now, I know it's not perfect, okay? The drawing of this is a little bit shady at best, but it doesn't have to be perfect. Even on your screens, it's not going to be perfect. On your papers, it's not going to be perfect. You do what you can, okay? We're not computers. From there, we can talk about where the y-intercept is. The y-intercept is where it crosses the y-axis, which is going to be when x equals 0. We can look at the graph and see that that is 8, or we can look at the table and see when x is 0, that y is 8. The asymptote, again, is where y equals 0, because it never actually goes below 0. You'll see that if you keep scrolling down that table, that those numbers do get smaller and smaller, but never actually reach 0. So our domain is going to be all real numbers. I'm going to shortcut this to do the pound symbol for numbers because I'm a little short on space. The range in this case is, again, y, because it's the range, and it has to be greater than, which is that symbol there, 0. Because y has to be bigger than 0. All the numbers that are here are bigger than 0. It'll never actually be anything equal to or less than 0. So don't be afraid on that to say that anything bigger than 0 counts for your range. You can see where that line keeps going up and up and up and up. That is important. Now, when we apply this to real world scenarios, it becomes a little bit more understanding. We'll do that on the next question. Here you'll see that I've truncated this. Truncated because it doesn't show the entire graph. It only shows a small portion. This is an old STAR question back from 2016. Okay. It says a portion of an exponential function is shown to the left. Find the domain and the range that is represented by this graph. Once again, domain is our x values. Those are our side to sides. And if I look really carefully at this, I see that yes, this graph does shoot way off to the right. So it does go off forever, getting bigger and bigger and bigger. However, I've also got a limit here. I've got a spot that says, I can't get smaller than this. This is the smallest I could ever be. And that number is -2. So when I look at that -2 here, I go, okay, x, you have to be greater than or equal to that -2. All right? Wrong thing. Go back. There we go. -2. Now, I am short on what I can actually do here. So I'm going back and adding the underlined part because it can equal -2. And we know that because the filled in circle means that the number is included. The hollow circle is where it's not included. The range, on the other hand, got a little bit of an issue. It's kind of in between, isn't it? It's not exactly 4, it's not exactly 5, but the point is it doesn't go beneath it. So I'm gonna say, and it's about 4.5, and that's what I'm gonna go with. Y is being compared to 4.5. And if you look at those numbers, they are again the ones that are bigger than it, okay? So it's greater than the 4.5. The question is 4.5 included with that answer or not? And in this case, because that circle being on it, yes, it is greater than or equal to, where any number that is greater than or equal to 4.5 will eventually be included inside this graph. And when I tell you real world situations make a little more sense when it comes to domain and range, this is why. The population of Mathsville is growing at a rate of 1.2% annually. The graph representing this function is shown to the left. That's this thing over here, okay? Find the equation for this example. Believe it or not, I need both the chart and I need the text in order to be able to answer this, okay? Because when I start solving these, I go, okay, y equals a, b, x. A is my y-intercept. I'm looking at my y-axis where x is 0 and saying, okay, if x is 0, what is my y? And I see that sitting at, again, I'm going to guesstimate. If you're working on the star, you can guesstimate a little bit too on it, okay? It's about 2.5. It's about 250,000 there. So when I go to write this, I go, okay, y equals 250,000 times our rate. Don't forget, this is a growth rate. That growth rate, going back to our equations from last week, if it is growing, it is 1 plus r. And that r is that percentage as a decimal. So I take the 1.2 and I push that decimal 2 places to the left and I go 0.012. I do 1 plus that, okay? I come here and I go, okay, 250,000. Will you let me tip back in there? Yes, you will. 1 plus 0.25 or 12 becomes 1.012. Close those parentheses, and that is going to be raised to the x. That x is going to be an exponent here. And that is going to be what my equation is. Y equals 250,000 times 1.012 raised to the x. Again, A is the y-intercept, B is the rate, that is either 1 plus r for growth or 1 minus r for decay, and in this case, it is growing, and then we raise it to an x. Make sure this is a decimal, okay? Now for the domain. For the domain, we're talking about the side-to-side motion. We first started tracking this in 2015. How do we know that? Well, because it says time after 2015. If there is 0 time after 2015, this is the first time that we started tracking it. This is where we're beginning. We don't look at the stuff from before. The graph only goes back to 0 because x is our side-to-side motion. It is 0 and bigger. That means x has to be greater than or equal to, so again, I'm locked into what stuff I can do, 0. And yes, or equal to means you underline it. Range is talking about the growing, right? Now, when I look at this graph, there is a minimum population that this graph is going to have. Eventually, we could work our way backwards in time and blah, 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 but that's not what we're given to work with. Where we start is, on an exponential graph here like this, is the 250,000. My y does start at 250,000, but since it is growing, it is going to be greater than 250,000. And no, you don't have to have the commas here. It's not going to help or hurt. It's just, I'm adding it so we can see what it is. And it is going to keep growing and growing and growing and growing. And again, we don't know what it's going to look like in the future, right? But in this case, our range is going to be our projected growth. Like how many people we have 20 years after we've taken this, and it's at 300,000, give or take. After 40 years, when it's 2055, we're at 400,000. To get to 500,000, it's 60 years later. Like, we can track what we expect that growth to look like and make predictions for the future. If you're ever wondering where we start getting some of the data about how viruses spread and such like that, or if we're looking at the data for how populations grow and trying to make predictions about what happens, we look at the growth rate for a couple of years and say, oh, it's about this per year. And then we write an equation like this and we put it onto a graph and into a table, and we go, oh, given this, the minimum population we're going to have is, and then it's going to grow at a rate of, so in about 60 years, we'll be at about so many people, okay? The domain in this case represents the number of years that have passed, because as those change, it allows us to predict the population based on this rate. You've got a worksheet in front of you. I'd like for y'all to get started.